not the color of light. We just use color because it makes the math work. And they can be red, green, or blue, but anytime you put them together, it makes white.
Do quarks make up protons, neutrons?
No, the electron and photon are fundamental particles.
Okay.
So I have these. They're also, each one has a neutrino that goes with it. So I have 3 generations of leptons, 3 generations of quarks. An electron is a kind of lepton. And then that's what there is in terms of basic particles. Then I have things that carry force between particles. And photons are the example of that. So I have a photon, I have a W, and I have a Z, and I have a gluon.
Okay, so for my purposes here...
That's all you got. That's the whole universe right there.
Okay, that's great. For my purposes here, the quarks make up the proton and neutron, right? Those are
right.
Okay, thanks.
Yeah, there's 2 kinds of stuff. Well, there's 3 kinds of stuff. There's these force carriers, and then there's the kinds of stuff. There's the electron side, which is the leptons, and then I have the quark side of things. Yeah.
Why are 2 of the quarks plus 2/3 and another quark, which is still a quark?
Right.
How were they called the same thing?
If he knew that,
And
he'd
yet
be
they're
applying.
given different, like,
If he knew that, he'd be applying for an orbital.
Okay, wow.
Well, no, it's
Just waiting for it.
that branch of mathematics is called group theory.
It's not that, of course.
It's way beyond. It's the way the math works out essentially, but that gets to an earlier question of, with the half charge, why just not make it 1? The answer is because the arithmetic, the mental arithmetic is easier if I do it that way. It's easier to think, okay, 2/3 minus 1/3 minus 1/3, that'll cancel out. 2/3 2/3 minus 1/3 will equal 1, and I can build them that
So
way.
you just make it work.
You
It's
pick.
kind of being defined by what makes it work.
Right, you could make those numbers anything as long as relative to each other they work out. So it's not 2/3 of anything. It's just that if I do that, then I get 1. And I really want to have an electron be -1 and a proton be +1. It just makes every life much, much easier whenever you get 1.
Is in physics, in fact, the application of quantification to the real world, and so it's all arbitrary anyhow?
Physics is the explanation for why the real world is. And I could express some of these things differently, but what they are is what the world really is. So I'm not saying, okay, I've got this funny view of the world that's incomplete or wrong, or it's not a shadow of the world. It really is a description of the world. There would be potentially other ways to formulate it. And through the history of physics, there are other, some of these branches started out with somebody having a different formulation that eventually was folded in because it's easier to keep everything consistent. But the underlying truths are the underlying truths. It's how things work.
So not to jump so far ahead, but since you have sort of mapped the landscape there, broad brush, where would you put this famous God particle in that mix?
Right here. So I have gamma WZG. So this is the thing that carries the electromagnetic force back and forth. So when I have my 2 charges next to each other and they're pushing apart, what's pushing? What's pushing is they're shooting photons back and forth. They're shooting these gammas back and forth, and that's pushing them apart. That carries the force. W and Z carry what's called the weak force, which we'll talk about later. The gluons carry the force of the strong nuclear force back and forth between these particles, keep them together. Mass, gravity, is the one thing that we've left out of all this. So there's got to be something, there's gravitons that carry that, but they're postulated, nobody's seen a graviton. But we have all this, we have this mass kicking around. Where does the mass come from? So this God particle is called the Higgs. It's an H. It's the only one that gets to be capitalized here. Actually, the W is capitalized here. The H that flies around, that H makes a field, and that field creates the mass for the particles. That's that God particle. Calling it the God particle was the guy who came up with that has since repented, and it was the biggest mistake he ever made in his life. Because, we talk about some of these things, this color, we use the funny words, charm and strange, and we don't necessarily realize that other people are listening. And you come up with kind of flippant things, and they turn out being part of the canon. Okay, so let's get quickly, we've got a few minutes left, we'll get to what an atom actually is, which is the first half of what we're supposed to be talking about today, but that's okay, we have a few more weeks. Okay, so I'm going to take these particles and I'm going to make an atom out of them. So, my atom has a nucleus, which has at least 1 proton in here, in the middle, and then it has an electron flying around outside. Okay. And that's the most basic atom. That's hydrogen right there. If I want to make more atoms, different kinds of atoms, I can start adding protons and neutrons in here. You would think, and then I need to add electrons out here because an atom has no charge if I'm away from it, which means that the number of protons I have in here has to be the same as the number of electrons. So here I've got 3 protons, which makes this lithium. And so now I have 3 electrons that are flying around outside it somewhere. And that's a different kind of atom, different element. Now, I added some neutrons in here because of part of the question that came up before. How does this proton stay together if the quarks are the same charge? They won't blow apart. Well, now I've got 3 protons in here. The protons are going to want to push themselves apart from each other because they're positive, positive, positive. What keeps them together? It's the same force. It turns out that the gluons can actually go outside of the protons. So when I have a proton, it has a whole lot of glue inside, and it's got some glue coming out of it as well. So they can't go very far. It's a short-range force, but it's very, very strong. Whereas the electromagnetic force, the charge force, is not nearly as strong, but it goes out forever. So if I add a couple of neutrons here, that gives me enough of this glue force, enough of this strong nuclear force, to hold the protons together and overcome the electromagnetic force. And I can do that because the neutrons are neutral. So they don't feel anything. They only feel the one force. They only feel that glue force. They don't feel the electric force that would push them apart. So if I start getting unstable in the nucleus, I can start adding neutrons to it, and then it becomes stable again. And that's mostly the topic of nuclear physics. That's really what nuclear physics is about. So I have this on the inside. I have the electrons on the outside. I have an awful lot of space here. If these things, if the nucleus were the size of a nickel, then where the electrons would be around the outside of the Earth. This is almost entirely empty space. There's nothing in here at all. So it would seem like if I've got these atoms, and they're almost all space, and I'm atoms, almost all space, I'd be able to put my hand right through physical objects. Why can't I just walk through the door if it's mostly empty space? The reason is because of this electromagnetic force. I have all these electrons. That makes a strong force field here. If I try to push in, my hand is made out of atoms that have the same sets of electrons flying around. And those electrons, when they get close to each other, push against each other, and I can't push through this thing. I can't get into that empty space. And that's really all it is. When I see a solid object, it's a wall of atoms. It's this wall of electrons on the surface of the thing. And I've got my wall of electrons, and when I push against it, I'm feeling those electric charges pushing against each other. And that's what, when it feels physical, when you touch something, when you push on something, you're not pushing the thing. The electrons at the edge of you are touching the electrons at the edge of it, and all you're feeling is that electrical repulsion of the things pushing against each other. You don't feel it here, because once you get a distance away, this negative charge cancels out with the positive charge here, so the whole thing's neutral. So if I walk far away, they kind of blend together. It looks like charge 0. But when I get close enough that I'm closer to this, and I'm further away from that, then I start feeling them. And that's why things feel physical. There is no such thing as a physical object. There's no structure. I can just push right through. If I can get through, if I can turn off that electric charge, I go right through it. The particles wouldn't do anything with each other. Yep.
You're using a two-dimensional blackboard to represent a three-dimensional concept, where the electrons circle the nucleus, they're not in the same plane, right?
Right, so let's, this is what the minimum I want to get through today is the answer to this question, so we'll do that. Now remember, these electrons are waves that move around like waves. So I've got my electron here, and it's not going around in a circle like this. It's actually wiggling around. It's not actually, but we're going to think of it this way. It's actually wiggling around in a wave like this. Okay? So this is the key thing. This is what the Nobel Prize was for here in discovering the atom, essentially. This wave has to line up with itself. So I go all the way around. I have to come back to right where I was the last time I was there. And it has to line up. I have to have an integral number of waves. 1 or 2 or 3 or 27 or 10,000. But I can't have 1.5 waves or 1.25 waves going through. Once I make that condition, because all these electrons have the same, the wavelength is the same. Right? It's just based on the mass of the electron. So once I say I'm going to use electrons to make my atom, then I know how big that wavelength is, and I can only put the electrons in rings that have an equal number, an integral number of waves. So this is what this picture is up here. If I look at on the top left, that's where I have 1, 2, 3, 4, 5 waves that fit in the circle. If I try to do it a different size circle, then it doesn't match, it doesn't line up. And I can't do that. The reason I have that on the board is because I can sort of draw this, but I can't possibly draw that and make it actually happen. So, achieve. So I have to change the size of the circle until it matches up, and I get the thing going around and around, where it's always in the same spot that way. So once I do that, I can do it with different numbers. I can have 3 waves, I can have 4 waves, 5 waves, 6 waves, all fitting in that circle. And what that means is that these rings, which you don't see here is to do that. See, in this picture, it's not drawn quite right. The number is changing, but the size is staying the same. So the size of the circle is staying the same. And so you see the wavelength is getting smaller. It doesn't happen. Right? The electron has its wavelength based on its energy. So what's really happening is these circles are getting bigger as I pack more waves in. That means that the electrons can only be certain distances away from the nucleus. I can't be anywhere I want to be. I can be at this distance. If I add one more wave, I have to go to this distance. One more wave, go to that distance. I can't be in between. It is quantized. There are specific places you can be. If I'm further away, remember this is positive, and then I have this thing which is negative out here. These things are attracting each other. So to get further away, I've got to add energy if I want to move into an extra wave. Now, if I get a bigger atom here, and I need to add more electrons, I can't put them all in the same place. So it also gets bigger just because all the inner parts are full. Right? No two things can occupy the same place at the same time. What it really is no two things with the same spin can be in the same orbit like that at the same time.
But are we really talking about neat orbits or cloud-like?
These are cloud-like, but this is the intuition that gets you there. And this is the Nobel Prize, the Bohr Nobel Prize for the atom, was this. It is not the cloud-like thing. It's just taking an integral number of things, of waves to go through. And if you do the math that I'm not going to do, you can write down very, very simply just the same orbital relationship that the moon uses to go around the Earth or the Earth around the sun. And once you put that constraint that you have to have an integral number of waves, you get certain what are called energy levels now, because I have to add energy to get over this attractive force between these two things. And when I add that energy, I get to that next energy level. And that's what the Nobel Prize was for.
But if the electron has no mass, theoretically, you can fit as many electrons as you want to in that one.
That's what Pauli got the Nobel Prize for in 1954. The electron does have mass, it's just small, but it doesn't have size.
Right.
Yeah, theoretically you can until 1954 when Pauli shows up. He says, I can't have two of these things in the same place at the same time with the same spin. And that's where spin comes in. So if I have two, okay, we're on these protons, now I've got helium. So I have one electron out here, I've got one electron out here. I can put them both in the same thing where they're with one wave going through, as long as this one is spin up and this one is spin down. The half up, half down, that's all I can do. If I want another one, I have to add a wave and go to the next shell, the next ring outside. Jane?
So do the protons in the nucleus have to balance out the electrons around?
They don't have to. In a normal atom, they do. If they don't, we call it an ion.
You call it a what?
An ion.
Oh.
And the difference between the ion and the atom, for practical terms, is that if they don't balance, then the thing is charged. So I can put it in an electric field, it's going to want to move. If I put it in a magnetic field, it moves, that sort of thing.
So, the spin up, spin down thing is kind of like how they pair, right? You can only have like one up and one down.
Right. And eventually we'll get to a point where we see in a magnetic field they do special things. But go ahead.
Okay, so we can't walk through walls.
Right.
We can walk through air and we can swim through water.
Right.
There are electrons there. Our electrons meet, but they're not being pushed out of the way. Is it a function of the number or why?
The whole atom's getting pushed out of the way. The difference between a solid and a fluid, and air and liquid are both different fluids, is that in a solid, all of the atoms are kind of locked together to make a thing. So I can't push one, it pushes on all the others. In a fluid, they're able to slide around by each other. So if I go through, I'm just kind of parting the seams. I'm just kind of pushing them to the side as I go through. And that's what air is. When I wave my hand through here, the reason you make wind is because all those atoms are being pushed out to the side, going somewhere else. It's a little water current. So and that really has to, water is halfway between where In a solid, they're all locked to each other, so they can't move without moving the whole thing. In a liquid, they're held together so they can't kind of bounce around anywhere, but they can slide around near each other. Can you, the force is weaker.
Can you explain why the air has atoms?
Why the air has atoms? Everything that's a physical thing is atoms. It's just a lower density. I don't have enough of them to get close enough that those forces hold them together. It's the same electromagnetic force that holds things together. Yep.
On these drawings in the bottom row, now is each bump a wave?
Each bump is one wavelength.
One wavelength?
Right. So I have a wavelength like this, and if I'm going to repeat this over and over again, I have to end up where I started out in order to do it. So I can take one and bend it around and it will match up. I can take two and bend it around and these will match up. But if I had 1.5 here, and I bend it around, it doesn't match up. So it's just how many wiggles I'm going to do as I go around. Go ahead.
So everything has atoms, and the density of those atoms determines the physicality of
The attractive forces between them, and most of these forces are short range, and so the how close they are they close enough for those short range forces to be able to take over and overcome the other forces that are involved. So the one thing I want to get to here is that I have these different things, these different orbits. They're different sizes. So I have one that's here and one that's here. And they have different energies because I have to overcome that electric attraction between the positive thing here and the negative there. That means I can talk about energy levels. So I can say how much energy I have if I'm in this orbit, and if I add energy and I push my electron out to here, how much energy do I have in that orbit? And then I write that down as energy levels. So I have the bottom energy level, 0. That's called the ground state, where I'm at as close as I can get. I have one wiggle as I go around. I can go into the next orbit. And then I have the first state there. And I can go into another orbit, and it gets higher. And this, as I go up, what I'm talking about here is the amount of energy the thing has, is increasing. As I add energy to this, I can push that electron into higher and higher orbits, giving it more wiggles as it goes around. As I get further and further out, these states actually end up getting closer together because the force of attraction here gets weaker as I'm further away. So I have to add less energy to get to the next one. And as this keeps adding, and that's just geometry, there's no physics in there, it's pure geometry. Or?
But as they get closer together, wouldn't the negative charges repel more readily?
They do, if I have more than one. But the orbit is also bigger, so there's more room for them to all be there. So I have these energy levels, and I can move back and forth between them. So I can go, when I go up, if I want to get up, if I want to add energy, how do I do that? I shoot a photon in here. Photons get energy, it's just a piece of light. The light comes in, and it'll be drawn like this. You label it gamma, that's what's coming in, and it takes my electron and it brings it up there. Now, what I said at the beginning is everything wants to get to the lowest energy it can. So once that happens, it'll sit there, it really wants to get back down, there's nothing stopping it, so it's going to come back down and it's going to shoot off a photon like that. That photon is going to be, if it's the same two states, the same energy that went in. That's what you see.
So is that why there's a limited number of elements in the element table?
That's next week, and that's because of what happens in the nucleus. The nucleus will get unstable. I'm still talking about here just hydrogen, one electron, one proton, and I can still move it to different energy levels there. Let's see here. We are out of time, although I'll take 5 minutes just to overcome
these different levels. The amount of time that it takes to complete this orbit, is that the same regardless of which level you're at?
No. Okay, so this is I'll end here with this. Although this is what the Nobel Prize was for, it is not actually what happens. So I just want to show you what it actually looks like, and then we'll break for today and come back next time. So we're called orbitals. That's these different shells that I'm talking about. I add energy, I get to the next one. I add energy, I get to the next one. This is what they look like. The first one is fairly simple. It's just that ball. It looks actually a lot like the thing orbiting. Now, quantum mechanics we'll do later. It doesn't move around. It kind of bounces around randomly all over the place. In fact, it's not even anywhere in particular. It's somewhere in that area. And that's the most you can say, is it's somewhere there. Or it's actually everywhere there all at the same time. until you go poking it. If you poke it, then you can see where it is. But until you poke it, it's just everywhere, kind of diffusely. So I have this one, the next one up, the next shell looks like that. It can be here, it can be there, it's bouncing back and forth between those two. It's disappearing, magically reappearing over there, but that's where the general area that it inhabits. And because I'm now further out, I've got more room to put these things. And there are 3 different shells at that next level. And then I start getting to crazier and crazier shapes as I add more and more energy.
A general question.
Yeah.
Thousands of years ago, the atom was identified.
Right.
What are the takeoff points that seem to allow this explosion in the 20th century to reveal all this type of information?
Basically just electricity and the ability to make a vacuum. Be able to suck the air out of a tube, and then once I have electricity, I can shoot electrons around and see what happens. And that's really all it was. The atom that was this classical idea of the atom is a logical construct. If I divide something down small enough, it must be the smallest piece, which is where an atom comes from. It's an atomic thing. That's not the same atom as the atom that was discovered and with the Nobel Prize in the 20s. It's a different atom. It's the same word, but it's really not the same thing. The ancient construct was not this physical construct. What I want to show you here real quick is we had just looked at this is what the orbitals are. This is a little bit more accurate for what they really look like. When I look at the ball, it's not actually a ball, it's not anywhere in that ball. There are spots where it's more and spots where it's less likely to be found. So it's kind of diffused, it's a little bit fuzzy. So these are slices through what we saw previously. So the idea here, I like this picture a little bit better, it's 2D instead of 3D, but it gives you that probabilistic idea that the thing is somewhere. If you really want to get fancy, you can draw pictures of it like this. There's a guy who sells these images. This is mathematically where the electron is. This is a fairly complicated one. This is way down the periodic table. There's lots of energy to get way out there.
So the proton is in the center of that?
The proton is in the dead center of that, is where the nucleus is.
Right.
And then the electron is that, all at the same time. One electron is in that whole big mess of everything, all at once. It's just a probability as to where you happen to find it at any particular time. Go.
Susan, will you be giving us any handouts and any chart of years of learning and
I'll see what I can do with what makes sense to hand out or take. We'll post some things where we can. Okay, so this is, we didn't quite get to all the whys that I wanted to originally. We'll make up for that next week. But hopefully you get a little idea of the flavor of things. It gets a little less practical, a little sexier as we go through. So if you stick with it, we'll get to the fun stuff. Increasingly fun as we go on.